Sri Gurubhyo Namaha. Welcome to our online project Ekalaiva. Already we are discussing about the solid state, and previous class we have studied about the properties of solids and the two different types of solids. We just saw the introduction of the two different types of solids and some of the characteristic properties. And today we are going to get into the detailed study of the two types of solids. And the two types of solids are, already you know that, crystalline solids and amorphous solids. And I told you also easily we can identify the crystalline solids and amorphous solids by the solubility test. Because crystalline solids are very well soluble in water, they have the definite geometry. So when they are just diffuse in water, they will get completely diffused due to the formation of hydrogen bonding with water molecule, so that they are very well soluble in water. Whereas amorphous solids, as they are fine powders, they are not able to, and the irregular arrangement of the particles will not allow the amorphous solids to form the hydrogen bonding properly with the water molecules, so that they will not be soluble in water properly. So they settle at the bottom as suspension, most of the cases, right? Now let us get into the detailed study of the properties of crystalline solids and amorphous solids. Crystalline solids, actually the building constituents of the crystalline solids are arranged themselves. Constituents means what? The particles. It may be ion, or it may be atom, or it may be a molecule. Okay, so the particles are arranged themselves in a regular manner. The arrangement of particles one after the other, it will be like a linear or layer after the layer. Okay, so it will be a regular arrangement pattern of the particles and the entire three-dimensional network structure, so that they will get like this. So this is an example for the crystalline solid where the particles are aligned properly, regularly. Okay, and then the regular arrangement will give the proper geometry of that particular crystal. And in existence of crystalline lattice, actually the lattice will be maintained. Now, let us check what does mean by lattice. It is nothing but the cell unit, actually the cell unit with a definite geometrical shape. For example, if you take this lattice crystal, this crystal has a lattice which has actually 1, 2, 3, 4, 5, 6, 7 and 8 spheres at the corners and one sphere in the center. Okay, so like this, the lattice points are combined, joined together with the help of a bond linkage, right? So it will be holding, that means the negatively charged particles and positively charged particles are just aligned properly, alternatively, to give a particular geometrical arrangement, to give a complete lattice. Lattice means you would have seen in the KG block. Okay, children used to play like a puzzle. Okay, so that is called a lattice, right? It will be like a square pattern. So they'll just go like a puzzle and find out the way. So that is how it will be having an interstitial space. The space where it is available as empty is called interstitial space, where the smaller sized particles can accommodate inside. And the crystalline lattice is a solid figure which has a definite geometrical shape with flat faces and sharp edges. As I said, it has the sharp edges. Okay, sharp edges, like means see 1, 2, 3, 4, 5, 6, 7, 8 corners are there, and the corners are connected by 3 edges. 3 edges connecting the corners. And how many faces are there? Usually when you take the cube, no, in cubical shape, there will be 6 faces. What are the faces? Top and bottom. Top and bottom, 2 faces, and lateral faces, 4 faces will be there. Okay, so totally 6 faces are there. And incompressible orderly arranged units, this crystalline solid will have incompressible orderly. Why it is incompressible? Because already the particles are aligned and there is no more space for the other particles to get inside, interrupt inside. So already the alignment is very stronger and alignment is compactly packed particles. Okay, so no more particles can enter inside and interrupt the structure. Okay, and then the arranged units are regular in manner. Definite sharp melting point. As the particles are arranged regularly, the sharp melting point characteristic property is maintained mainly by the crystalline solids. Okay, at a particular temperature they started melting. Then there will be no any deviation for that particular solid to melt. Anisotropy, we will discuss in detail what is meant by anisotropy. Due to the arrangement of the particle, the other physical properties will get vary. Let us see what is that. And definite geometry, that is what already we have seen, that the particles arrangement will give a definite shape of a particular crystal. And it gives X-ray diffraction bands. When X-ray is passed into that crystal particularly, then the deviations will occur and then the band of spectrum will be formed. Okay. And examples for that crystalline solids, NaCl, very common usage at home, that means in kitchen. That means table salt. What do we call it as? Table salt, which is NaCl. So if you take this crystal, we have the lattice points like sodium lattice point, and the smaller red ball will be chlorine. Okay, so like that. Positively charged and negatively charged particles will be aligned together, so that we will be getting a complete lattice. Right, and this is an example for cesium chloride lattice. Are two examples for the crystalline solids. And the next type of solid is amorphous solids. Amorphous, the term is new actually, because already we are familiar with the crystalline solids which are soluble in nature, whereas amorphous is the word derived from the Greek word amorphe, which means that shapeless. There will be no regular arrangement of the particles. They don't have the regular distinct boundaries. Okay. And no regular, which means that the shape is not regular and haphazard arrangement of the atoms or molecules. The constituent particles may be atoms or ions or molecules. So those particles will not be aligned properly in the regular manner, so that they will have some deviations in the physical properties when we learn. And also considered as, these amorphous solids are also considered as non-crystalline, as they are fine powder. They will not be looking like a crystals. Crystals means you could feel the roughness over the fingers when it is rubbed, isn't it? So that crystalline nature will not be shown by this amorphous solids, and also they can be called as supercooled liquids. What is meant by supercooled liquids? Let us take example, old monuments which contains the glass windows. If you see the glass windows, you could feel the difference what we have at home and the glass windows at the monuments. You could see the thickness at the bottom of that glass, and then it will be thin on the top. What is the reason for that, if you think? No, actually it is an amorphous solid which started melting at a particular temperature. Beyond the temperature, if it goes, no, the glass started melting and then get settled at the bottom, so that at the bottom you could see the glass window will be thicker, and at the top it is so thin. So such a property is exhibited by the amorphous solids, so that they can be otherwise called as supercooled liquids. And as they do not have the regular geometrical shape due to the irregular pattern of arrangement of the particles, they do not maintain sharp melting point. Okay, at a particular temperature, that means after a certain temperature got over, these amorphous solids will get softened. Okay, if it becomes so softened, will it be soluble in water? Of course no, right? So the solubility will be decreasing. And isotropic, iso means same. The physical properties will be exhibited by these amorphous solids. Okay, iso, same, right? No definite geometrical shape because of the irregular pattern of arrangement. If you look at this structure, you will be able to understand that how the particles of amorphous solids are arranged. See here, there is no regularity, and the bond link, see if you check, no, the atoms are free somewhere, isn't it? Which shows that the irregular pattern of arrangement in case of amorphous solids. And they do not give X-ray diffraction bands. Bands will not be produced by this amorphous solids as they are soft in nature, and also they are opaque also, that's why. And examples, we can take glass, rubber, plastic. These are all the examples of amorphous solids. So when we started learning the properties of the amorphous solids, you come to know that how they are different from the crystalline solids. Now let us come to the important topic, isotropic and anisotropic nature. So anisotropic nature, which is the property exhibited by normally crystalline solids, anisotropic. Okay, so what is that? Anisotropic nature implies that certain physical properties like electrical resistance, resistant towards the electricity, and refractive index, these values will be showing different magnitude. When we study the physical properties like electrical resistance and refractive index, the values, magnitude which we get through the study of that means crystalline solids, it will be giving different values when measured along different directions in the same crystal. So the crystal will be the same. For example, if you take crystalline solid like NaCl, sodium chloride, which contains Na plus positive lattice, Cl minus negative lattice points will be there. So if you look at the structure of this NaCl, sodium ion, chloride ion, sodium ion, negatively charged ion and positively charged ion, they are just aligned. Okay, so if you go in any direction, if the properties are same, if the magnitude of the properties are same, then we can say that solids obey isotropic nature. But here actually the different arrangement of particles you could see. Why there is different, that means there is a variation in magnitude of the physical property. It is due to the different arrangement of particles in different direction. And here we have two different arrangements of the particles. One, as we come down vertically, okay, as we go up or as we come down, you could see all the smaller particles are aligned in one row and all the larger particles are in one place, isn't it? And as we move from left to right, or that means from bottom to the top, okay, the particles are alternate. That means larger size particle, smaller size, larger size, smaller size, like that. There is an alternate arrangement of the particles. Due to this different arrangement of the particles in this crystalline solids, it will show different values over the physical properties like refractive index, electrical conductivity, all the resistivity, all that things. Okay. So this is what mean by anisotropic nature of crystalline solids. Next, isotropic nature. Of course, it is exhibited by amorphous solids. Amorphous solids will exhibit this kind of property. So why this kind of property is exhibited by amorphous solids? Actually, it is due to the irregular arrangement of particles in all the directions. If you go anywhere in this, there will be alternate arrangement of the particles like this. If you go horizontally or vertically, whatever it is, the arrangement of the particles are actually one after the other. It is irregular. Okay, it is not that one larger size and one smaller size, one not like that. The arrangement is totally irregular in nature throughout the solid crystal, isn't it? So that due to this irregular arrangement of particles in all the directions, they show various physical properties are same in all the directions in the same crystal. This is the one crystal of a solid. where if we go in any direction, the particles show irregular arrangement, and this irregular arrangement will implies for the various physical properties values are same in all the directions. Is that clear? In the same crystal. Next, let us, with all the studies what we have learned so far, let us come to the conclusion of differentiating the crystalline solids with amorphous solids. So, crystalline solids, they have definite geometrical shape, whereas amorphous solids are irregular in shape. Whereas in crystalline solids, the particles are arranged regularly. And they melt at a sharp and characteristic temperature, which means these crystalline solids have sharp melting point, whereas amorphous solids will become softened over a range of temperature. That's what I told you. When the temperature beyond, okay, at a certain temperature, the amorphous solids will become so softened. And when cut with a sharp edge tool, these crystalline solids will split into two pieces, and the two pieces will be having a regular arrangement. That means regular and plane, okay, and the planes will be smooth, surfaces will be smooth, right? And they have definite and characteristic enthalpy of fusion. Fusion means what? When solid is getting converted into the other phase. So what happened? It will be having the definite, because of the definite geometrical shape, they will be possessing the same characteristic property also, even as an individual particle. Now, but these amorphous solids, when they are happen to cut with the sharp edge tools, they cut into two pieces like crystalline solids, but they have irregular surface. That means the newly generated surfaces, that means the planes will be irregular in nature, and they will not be soft also. That means smoothness will not be there. Rough surface only will be produced. And they do not have definite enthalpy of fusion due to the irregularity in arrangement. They do not have the definite enthalpy of fusion. And of course, it is anisotropic in nature. Which one? Crystalline solids are anisotropic in nature, whereas amorphous isotropic in nature. Crystalline solids maintain the property. Stability is maintained, isn't it? So they are called as true solids. So when they are dissolved in water, they produce true solutions. Okay, that's why crystalline solids are considered to be true solids. Whereas amorphous solids, over a particular range of temperature, it will be converted into soft solids, isn't it? So they can be called as pseudo solids. They are not real solids actually, as they just change the characteristic property over a range of temperature. So that, or else they can be otherwise called as supercooled liquids. For example, glass you can take, which is considered to be amorphous solid only, but it is a supercooled liquid. And long range of order, that means the arrangement of particles is a long range of order of arrangement, whereas in case of amorphous solids, it has a short range of arrangement. The order of arrangement will be very short range, which means that what? The irregularity will be seen throughout in all the directions. We could see the irregular arrangement of the particles actually in this case. Now, let us come to the point why amorphous solids are called pseudosolids or supercooled liquids. Amorphous substances are usually termed as pseudosolids or supercooled liquids because of the ability like glass to flow. Okay, like glass, no, these amorphous solids will start melting and just get thicker over the bottom and thinner over the top, right? So the appearance, that means the glass tends to become milky in appearance over a long period of time, and this is because the slow crystallization of glass. That's why glass is amorphous solid, but it is not maintaining the actual amorphous nature throughout, isn't it? That's why they are considered to be pseudosolids or supercooled liquids. For example, amorphous silicon, which is a supercooled liquid, or it can be called as pseudosolid, which is used to make photovoltaic cells. Voltaic cells, which is generated by using energy, sunlight. Okay. So today we have discussed about the crystalline and amorphous solids differences, and we have learnt almost all the properties, and we have to go beyond the properties, other physical and chemical properties of crystalline and amorphous solids. Let us see in the next class. To get more videos, please subscribe our channel to get the latest update. Thank you.